Hello, Algebra. Good to see you. Happy Monday. We are going to keep rocking and rolling. You did great with that long section of 2.1. Now we're going to look at operations with complex numbers. So, section 2.2, here we go. Here's your learning target. I can identify, add, subtract, and multiply complex numbers. We're also going to talk about division of complex numbers here at the end. And success criteria, you will be successful when you can identify parts of complex numbers and apply properties of equalities. All right, so take a second, pause if you need to. We're going to start today by solving an equation, all right, to see what exactly a complex number is. So when we've solved our quadratics, we've run into real solutions. We've run into two real solutions. When you take a square root, you have to have a positive and a negative solution. We've also run into taking the square root of a negative number where, again, we have a plus or minus, but maybe it's like plus or minus 2i or plus or minus I times the square root of 3, right? So now we're going to see what happens when you combine worlds, all right? So let's just start by solving the simple quadratic. If you want this example in your notes, feel free to get it down. First, I'm going to minus 16 from both sides. It's going to cancel out there. I'll be left with x minus 5 quantity squared equals negative 16. Again, I can't do anything with that negative 5 or the x on the inside quite yet, so I'm going to just square root because all of it is being square rooted. Or it's all being squared, so to undo that, I'm going to square root both sides. That's what I meant to say. That's going to cancel out there. I'll be left with x minus 5. That was what was in the parentheses, right? Equals plus or minus 4i. Again, I is an imaginary number. Since we're taking the square root of a negative number, I can kind of think about separating that negative 16 into 4 times 4 times negative 1. That should be a 1, not an I. Again, we know that, well, there's a group of 2 underneath the radical there. I'm just explaining a bunch of review from last week as well. There's a group of 2 under the radical. That's why I can bring out 1, 4. And the square root of negative 1 we know is I. So I'm just kind of jumping down into square root of negative 16 plus or minus 4i. And then we need to add 5 to both sides. So as x is going to be equal to 5 plus or minus 4i, all right? Notice that this isn't a real number because we have that imaginary number there. It's not quite fully imaginary though, because again, we have a real part to it. So that is what is considered a complex number. All right, so definition of complex numbers here. I'm going to draw a little Venn diagram as well. So here is all of my real numbers. So real numbers are things we've been working with since first grade. Things like 2 or 1/2 or 4/5. Maybe a real number is 0.9997 or square root of 7. Square root of 7, it's a crazy number, but it's still technically real. I'm going to add one more in there. Pi, 3.141519, it keeps going on forever, right? But it's still technically a real number because there's no imaginary part to it. On the other hand, we could have our imaginary numbers. And that is what we saw with the last section. We could have I, we could have negative 6i, we could have 2.4i, we could have I times the square root of 13. Again, those are all imaginary numbers. I'm going to try and find a nice purple. I like color coding things here. If I wanted to combine real and imaginary numbers into one giant world, I could call them complex numbers. So complex numbers are a combination of real and imaginary. So just like what we saw earlier, we had 5 plus 4i. We also had, again, since we square root, we could have two solutions. We could have 5 minus 4i. All right, so what about 2 plus I? Or 3 minus 1/2 I? You're noticing that there is a real part. I'm going to highlight the real part in yellow on all of these complex numbers. And there's an imaginary part. being highlighted in green of all of these complex numbers, all right? So complex numbers have, so I'm going to continue this over here. Complex numbers are in the form a plus bi, where a is the real part, and over here, b and I, that is your imaginary part. Take a second, write down anything if you need, pause if you need to. I'm going to go back to that Venn diagram as well. All right, so how do we deal with these things? If we're trying to like combine these, you do not need to write this down. Do not worry, but this is just a reminder from everything that we've talked about since, like, you know, again, 5th grade math, right? Commutative property says that a plus b is equal to b plus a. You can also apply this to multiplication. A times b is equal to b times a. Associative property means you can group things and still get the same result, all right? So just kind of read through these. Identity property as well. The sum of 0 and any number is just the regular number. I mean, these are things that you know. These are things that make sense, like a times 1 is equal to a, all right? And the distributive property, all of these things still apply to complex numbers, all right? So even though they look crazy, they've got imaginary parts, they've got real parts, they're gonna generally work the same. All right, so here's kind of a little definition of adding and subtracting complex numbers. I'm gonna run through it real quick. If you were trying to add two complex numbers, here's an example of one complex number. It has, again, a real part and an imaginary part. And here's an example of a second complex number that we are adding to the first complex number. Again, it has a real part and an imaginary part. Right now, we're just letting these A, B, C, D be parameters because we could be, again, adding any complex number. If you wanted to combine these, all you do is just add the real parts together and add the imaginary parts together. It's that simple. So here's going to be a quick example. Do I have one underneath here? I do, all right? So if I wanted to add a complex number, 3 plus 9i, to 2 plus 3i, all I would do was add the real parts together. So I'm going to say 3 plus 2, and I'm going to group it as well so we can see exactly these two distinct parts of the end complex number of this sum. And I'm also going to add the imaginary parts together as well. So it's going to be 3 plus 2 plus 9 plus 3i. Again, the imaginary part has to have the imaginary number with it. And then we can simplify here. 3 plus 2 is 5 plus 12i. All right? Pretty simple. Not too bad. We can just add these suckers together. Call it good. All right, subtracting complex numbers is a little bit different. So when we subtract complex numbers, I think the easiest way to understand this is if we take care of that negative. I'm going to do an example off to the side. Do you remember when we used distributive property and we had a negative outside of the parentheses and maybe it was negative x plus 3, right? When we had that negative on the outside, it just said distribute it to both of those terms, because technically it was like a -1, so we'd be multiplying by -1 to both of those terms. Anyway, that entire expression would turn into negative x minus 3. It just changed the sign of everything on the inside of the parentheses. So if we could think about subtraction as taking care of that negative with these complex numbers, then we can just combine things in the end. So what I'm going to do is take the negative that's on the outside, distribute it to both of these terms, both of the parts of my complex number. That first part, the 3 plus the 9i, that first complex number didn't really do anything, right? Didn't change. But we're going to change the sign of everything that's on the second complex number since we are subtracting it. So this is going to turn into -2, and instead of plus 3i, it's going to be -3i. And now I can just combine things like regular, all right? So I've got a real part, the 3 and the negative 2 is going to combine to be 1, and I have a positive 9i and a negative 3i is going to combine to be a positive 6i. All right, so that's the best way that I like to explain subtracting complex numbers. Take care of that negative on the outside like it's just regular distributive property, and then you can combine like terms if you want to think about that. Okay, multiplying is going to look very similar. Have you guys heard of FOIL before? First, outside, inside, last. And we were doing that a lot when you were like simplifying quadratics and stuff. It's going to be the same type of thing. So you're going to multiply complex numbers the same way you would multiply x plus 1 times x minus 3, right? You would multiply the x's together. That's the first term of each. You would multiply the outside numbers. You'd multiply the x and the 3 together. Then you would take care of your inside numbers, the 1 and the x, and then you would multiply the last numbers together, all right? If you have questions about the FOIL process, let me know. Otherwise, this should look familiar. So what I'm going to do is I'm going to multiply the negative 4 and the 2 is going to be negative 8. I'm going to multiply the negative 4 and the positive 3 is going to be 3i is going to be a negative 12i. All right, don't forget that imaginary part comes with it, because as soon as you multiply a real number and imaginary number, it kind of turns into an imaginary number. All right, now I'm going to look at multiplying the 7i to the 2i is going to be a positive 14i. And then the 7i to the 3i is going to be plus 21i squared. Since I'm taking I and I'm multiplying it by itself, it's 7i times 3i. It's going to be 21i squared, all right? So what is that going to look like if we start to simplify this down? And I wrote it in 2 different colors so you could see exactly, the parts, the steps to that FOIL method. So if I start adding these together, where's my like terms? The negative 8, it's a real number. There's no other real numbers in this. They're all either imaginary or I squared, and we'll talk about that in just a second. So we can't do anything with the negative 8. Negative 12i and a 14i can combine to be a positive 2i. Let's talk about that 21i squared now. If you remember, I is the square root of negative 1, and we talked about before, if I let I squared, that essentially is just squaring both sides of this equation, right? That square and the square root would cancel out and give you negative 1. So I squared is equal to negative 1. In here, I have I squared. I can just substitute that with negative 1. So if I had to rewrite this, I'm going to rewrite it one more time. It's going to be negative 8 plus 2i plus 21 times negative 1. And I'm running out of room a little bit, so I'm going to take it over here. I'm going to change that sign of the 21 because I'm multiplying by a negative 1. So it's negative 8 plus 2i minus 21. And now I suddenly have 2 real numbers. I have the negative 8 and the negative 21. Those are going to combine together to be a negative 29. Still with the imaginary part of plus 2i. And that is how we get another complex number from multiplying 2 complex numbers together. Again, it has that real part of negative 21 or 29, and it has the imaginary part of 2i. All right. Okay, we have added complex numbers. We've subtracted them. We can now multiply them using that FOIL process. Let's talk about dividing complex numbers, because that is also just slightly different. All right. I'm going to have you recall last week when we rationalized the denominator. Last week we took an expression that may look like 3 over square root 2 to rationalize that, because we don't like square roots in the denominator. It just doesn't make sense. How can we divide a pie into square root of 2 pieces when that's not even like a nice number, right? So what we did is we multiplied by the denominator by a new number in the top and the bottom, right? So we would multiply by square root of 2 over square root of 2, which essentially is just multiplying by 1. Because it has the same numerator and denominator, it's essentially an entire whole. So that would give us 3 times the square root of 2 over the square root of 4, which we then could simplify down with a real number in the bottom. So square root of 4 is 2. We planned it that way so that we would get a real number in the bottom. We're going to do the same type of planning, if you think about it, when we're dividing complex numbers, because we need to make sure that our denominator is a real number, all right? Again, how can we divide a pie into 2i pieces? That's just not going to work. So, to simplify two complex numbers that are being divided, we're going to kind of go through the same type of process that we did rationalizing the denominator, but we're going to be using what is called the complex conjugate. So a complex number we know looks like a plus bi. If you were taking a complex number and you wanted to find its complex conjugate, sometimes you could even think about it as like the opposite. The complex conjugate of a plus bi is a minus bi. The only difference here is that the sign of the sign of the imaginary part is now opposite. So for example, if we had a complex number that was 2 plus 3i, its complex conjugate would be 2 minus 3i. If we had, I'm going to do just a couple examples here. 4 plus I, if that was a complex number, its complex conjugate would be 4 minus I. I'm going to do a couple more. If we had a complex number that was negative 5 minus 9i, its complex conjugate would be negative 5 plus 9i. All right? Any and all examples that you need to get down, please do that. Again, all that's changing is the sign of the imaginary part. So here it was a positive I, now it's a negative I. Here it was a negative 9, now it's a positive 9i. Okay, so we're going to use the complex conjugate in this process of dividing two complex numbers. So here I have two complex numbers being divided by each other. This would be a good example to get down. We have 3 minus 4i being divided by 5 plus 2i. Remember when we rationalized the denominator, we multiplied by 1? And sometimes that 1 looked like square root of 2 over square root of 2 or square root of 15 over square root of 15. Essentially, it was still considered just 1. We're going to do the same thing, but now use the complex conjugate of the denominator. All right? So I'm even, you know what? I'm going to write some steps off to here. To simplify dividing your complex numbers, multiply by the complex conjugate of the original denominator. All right, so my denominator here is 5 plus 2i. Its complex conjugate would be 5 minus 2i. So that's what I'm going to multiply by in the top and the bottom. Again, if I plan it like this, essentially all I'm doing is multiplying by 1, so it won't change that original number, right? Okay, let's simplify to see what we get. So this is going to turn into a giant multiplication problem. This is essentially equal to 3 minus 4i multiplied by 5 minus 2i over 5 plus 2i over 5, or multiplied by 5 minus 2i. Again, when we multiply fractions, you just multiply straight across. So we have a multiplication problem in the top and one in the bottom. Okay, so let's just multiply these guys. It's going to turn into a mess, but it's going to be all right in the end. So I'm going to take the FOIL process, multiply in the top. This is the 3 times the 5 is going to give me 15. 3 times the negative 2i is going to be negative 6i. All right. Now let's do that second part. So negative 4i times 5 is going to be a negative 20i. Negative 4i times negative 2i. Okay, negative 4 times negative 2 is a positive 8. And we have two i's that are being multiplied to each other. So it's a positive 8i squared. All right. So after we foiled the top, it looks like 15 minus 6i minus 20i plus 8i squared. All right, let's look at the bottom. And I'm going to do the bottom in purple. So the denominator here, again, FOIL it just like regular. 5 times 5 is 25. 5 times negative 2i is a negative 10i. Let me get rid of those arrows so we don't get mixed up. 2i times 5 is positive 10i. And 2i times negative 2i is a negative 4i squared. Okay, again, let's see what we can simplify. Let's see if we can combine any like terms on the top and the bottom. All right, I'm doing this as one giant chain. I'll show you it all at the end. So now we're here. What can I combine on the top? Well, the 15 doesn't have any real numbers to combine with, so I'm just going to leave it as 15. The negative 6i over here and the negative 20i can combine to be negative 26i. Let's look at that last term, which is the positive 8i squared. Again, we know that I squared is just equal to negative 1, so I could even write this. Let me make sure I'm in the right, there we go. I could even write this as plus 8 times negative 1. All right. Again, let's look at the bottom here. And I'm going to try and highlight things as we go. So the 25 doesn't have any buddies to be with, so just 25. But take a look. When we multiplied by the complex conjugate of that original denominator, now we've got 10i and negative 10i, or negative 10i and positive 10i. They're going to cancel, right? So boom, that already gets rid of the negative part in our denominator. And all we're left with is the negative 4i squared, which again, negative 4, and the I squared is really just negative 1. Let's continue to simplify this. I'm just taking this step by step. In the numerator, 15 minus 26i, I'm just going to make that 8 negative. In the denominator, I'm just going to multiply the negative 4 and the negative 1. So I'm going to have 25 plus 4. I'm keep moving along here. The 15 and the negative 8 are going to combine and be 7, but I still have the negative 26i over 29. And that is as simple as you can make it. Let's actually go one more step further. So this technically isn't a complex number right now because we haven't written it as a real part and an imaginary part. We're thankful that we don't have an imaginary number in the denominator, right? If we wanted to write this as a real complex number, well, my real part would be 7 over 29. Again, I'm breaking up this addition, but I still have to use those denominators of 29 there. So the real part would be 7 over 29, and the imaginary part would be minus 26i over 29. So there, it looks crazy, but technically it is a complex number because we have the real part and we have the imaginary part. Okay, that was a lot. That was the whole process. Go to Blackman 107. I will see you there. All right, rock on. We'll go over some more examples as well. Bye.